Hi, in Chapter 4, we're going to explore dimension, application, and limits of size. Some of this is going to be a review for you, but just that. The objectives are to clearly apply dimensions by complying with the stated general dimensioning guidelines. Again, review. And number 2, apply dimensions to any of the geometric shapes commonly found on mechanical parts. And 3, cite the categories for limits of fit and describe their general condition created by each category. Then we're going to introduce rule number 1 and rule number 2 of GDT as ASME Y14.5, and then we're going to provide examples. Definitions: regular feature of size. That's a single size dimension. That could be a thickness, a width, a length, or diameter. So when I want you to think of feature of size, I want you to think of, something that has a limit of size, like a slot width, overall length of a part, a diameter, something you can touch. Here's how you would dimension a cylinder. The diameter and the length are required. Preferred dimensions: we prefer to put the dimensions on the non-circular view. Only one view may be necessary for a cylinder. A basic rule of thumb is when you're creating drawings, you need to put enough views on there to completely define the part. And then with a cylinder, you could probably get away with just one view. So in this case, the length dimensions are shown here and the diameter dimensions are shown there, and we have the symbols that designate these as diameters, so you don't really need this other view. To dimension holes, you must have the diameter, the location, and the depth if it's required. Now, through holes don't require a depth. So here's some examples for dimensioning a hole. In this case, we got the diameter symbol, 3 inches. We have the dimension line, and it's on the inside of the part. In this case here, we have the dimension outside of the part. And then here we're talking about a tube shape, a hollow tube shape. We have the ID dimension like this, and we have the OD. So, notice where the arrowheads are and how the dimension lines are structured on these parts. Now in this particular case here, we have the diameter symbol, but we don't have the other arrow on the other side. Over here we're dimensioning a counter bore. We're not showing the depth on that one. So location. Locate the dimension to the hole center. Center lines and extension lines should be used. Center lines between holes and extension lines beyond the holes, and dimension on one side of the view. Okay, here are some examples. You can see our locations are dimensioned to the center of the holes, in these cases right here, and we're dimensioning the location of the holes in the view where you can see the hole. Okay, so these are your basic rules. Again, this is a review. Now for depths of holes, assume to go through the part unless a depth is specified. When it's not really clear on the drawing, use the designation through. THRU is acceptable. For blind holes, you need to use the depth symbol, and then depth specified after the diameter, so the diameter always comes first, and the depth is the distance to the full diameter. When we say full diameter, what we're talking about here is we have a blind hole and the depth is dimensioned to the full diameter. Now, drills, unless they're special bottoming type drills or end mills, for instance, will have a point. So what happens is that the point is not dimensioned. The depth is based on the full depth of the hole, not to the depth of the point. So what we have here, we have 2 holes So the 2 by is the number of holes, diameter 0.375, and then after the diameter comes the depth symbol. There's the depth symbol, it's an arrow pointed down. Past practice used DP, but we want to use the depth symbol. Again, this should be a review for you. A counterbore. A counterbore is a stepped increase in the diameter of a hole. It's used usually to recess a screw head. To completely define a counterbore, you must specify the diameter of the counterbore, the depth of the counterbore, and then the radius at the bottom. This is that fillet radius at the bottom. So here are some examples of dimensioning a counterbore. In this view, we have the diameter 250 through. We have the counterbore symbol, the diameter of the counterbore, and the depth. And then finally in the last line, what we have is the R.06. That's the fillet radius at the bottom of the hole. There's several other ways. In this particular case, we dimension the depth of the counterbore. We use the counterbore symbol, and then we have the depth here. The other way to do it is to put a dimension on the remaining thickness of the hole past the counterbore. In some cases, it depends on, you as the mechanical designer may want to control this depth more than you want to control the depth of the counterbore. So this thickness can be dimensioned separately. So in this particular case, we don't use the depth symbol on the counterbore because that's dimensioned over here. Lastly, for this video, I'd like to talk about a countersink and how to dimension a countersink. A countersink is an angular increase in the diameter of the hole. It's usually to recess a flathead screw. To completely define a countersink, you must specify the breakout diameter and then the angle. So that's the diameter at the top of the chamfered hole. So in this case, we have the diameter symbol, 0.250 through. We have the countersink symbol, the diameter of the countersink, and then the symbol that says by 82 degrees. So that's how we dimension a countersink. I'm going to stop here and pick it up in the next presentation.